Welcome back to my channel. Our lesson today is about work and power. Firstly, we will study the definition of work. Then we will study how to calculate the work of gravity and the work of a spring. We will learn their formulas and how to apply those formulas. Then we will study the work kinetic energy theorem. After that, we will study the definition of power and the formulas used to calculate power for some different cases. Firstly, what is work? Work in real life is different from the term work in physics. Work in physics means the ability of the force to displace an object in a parallel direction. Or you can say that it's the process of applying a force through a distance to change the energy of an object. Work is calculated by multiplying the force and the parallel displacement of that object. Or you can write it as F average delta D times cosine theta. We multiply by the cosine to take the parallel component of the displacement. Work is a scalar quantity as it results from the dot product of force and displacement. Positive work is associated with an increase in speed, and negative work means that there is a decrease in speed of that object. A decrease in speed means that the force is opposite to the direction of motion. To understand any new concept, I prefer to start with the examples. In the figure above, mass M is being pulled horizontally to the right by force F. This is force F, inclined at angle. Force F and its components are shown in the diagram. This is the horizontal component and this is the vertical component. F cosine theta and F sine theta. The surface is rough, so we need to include the friction. Friction F opposes the motion. Determine the work done by the applied force, work of force F. Work of force F is equal to the force times delta D parallel, the parallel displacement. Then it is this component, the horizontal component, because this is parallel to the direction of motion. Then work F equals F delta D cosine theta. We could apply this formula directly, the formula that we studied in the first slide, because you get the parallel component when you multiply by the cosine, as you are given the angle with the x-axis. Okay, let's go back to our example. B, determine the work of friction. The work of friction equals the friction force times delta D cosine theta. It's better to directly apply this formula. Cosine theta between the displacement, which is to the right, and the friction, which is to the left, is cosine 180. Because friction is opposite to the direction of motion, this is F delta D times cosine 180. Cosine 180 degrees is negative 1. Then this is going to be negative F delta D. So the work of force F equals F delta D cosine theta. The work of friction equals the friction force negative times delta D. C, determine the net work net. You can calculate the net work by two methods. Firstly, work net equals F net, the net force. If you calculate the net force, then you can just substitute in the formula, times delta D parallel, or delta D cosine theta again. F net is F cosine theta minus F. This is the net force and the axis of motion. So it is F cosine theta minus friction. This is how we find the net force. Times delta D parallel. Another way to find it is by adding the works we calculated. This is F delta D cosine theta minus the friction times delta D. The two works we got here. This is equal to, if we take delta D as a common factor, this is F cosine theta minus F times delta D, and it's the same. And always we substitute with the parallel displacement. Now let's apply this formula for more specific forces. The work of any force is calculated by multiplying the average force times delta D parallel. If we want to calculate the work of gravity, we need to consider that the force of gravity is a constant force as you are close to the surface of Earth. Then F average is equal to the force of gravity at any point. It's the same value. Then it is equal to m times g. And the displacement is the change in height of that object as the gravity affects vertically. So the work of gravity is mgh, while m is the mass, g is the acceleration of gravity. It's equal to 9.81, but for the SAT test we use it as 10 meters per second squared because you're not allowed to use a calculator on the SAT test. And delta h is the change in height of that object. Let's prove that by solving this example. In the figure above, mass m is positioned at the top of a frictionless incline with an angle of theta. The mass slides down the incline a distance delta d. This is delta d, the incline distance. Determine the work done by gravity. Work of any force equals that force, Fg, work of gravity is equal to Fg, the force of gravity, times delta d parallel. The parallel displacement is this displacement, the inclined one. The force Fg is decomposed to two components. A parallel component, this is Fg sine theta, and this is Fg cosine theta. If we consider this angle as theta, this angle is equal to the angle with the ground. So the parallel force is Fg sine theta. Delta d parallel is delta d, the distance. Now this is equal to Fg m times g. This is Fg. Sine theta is the opposite, delta h, over the hypotenuse, that's delta d, times delta d. These two cancel out, so it is mg delta h again. So you can forget all of this and apply the formula of work of gravity. Work equals mg h, or delta h, the change in height. Then you can say that the work of gravity is m times g times the difference in height, and don't consider the inclined distance of the object. So if the height of the incline is 10 meters and the mass is 2 kilograms, then the work of gravity is equal to m, that's 2, g is 10, and h is 10 again. This is 200 joules. The unit of work is joule. The unit of work is the unit of force, Newton, times the unit of distance, and that's meter. Newton times meter is the joule. Now to calculate the work of a spring, we use the same formula. The average force times delta d parallel. But here the elastic force of the spring is a varying force. If you look at the graph of the spring force and the displacement, you see that it is a linear graph and it is varying. So simply the average of this force is half of the maximum. Then we can say that the work of a spring is F average, that's half of the force of spring. The force of a spring is K delta x. This is Hooke's law. If you want to take its average, you multiply it by half because it's half of the total force. Half K delta x times delta x, or delta d. which is the displacement of the object, but we like to make the symbols the same. Then the work of the spring is delta, the change in half kx squared. Half kx squared final minus half kx squared initial, while k is the spring constant and x is the displacement or the change in length of the spring. A 4 kilogram mass, this is M, 4 kilograms, is attached to a spring with a spring constant of 20 newtons per meter. This is K, 20 newtons per meter. The mass is lowered 0.5 meters to equilibrium. So when the spring is attached to the mass, the displacement is 0.5 meters. This is X. Where it remains at rest, how much work was done stretching the spring? Let's go directly to the formula. Work of the spring is delta half kx squared. So this is half kx squared final minus half kx squared initial. The spring was not stretched or compressed at the beginning, so the displacement at the beginning is 0. Then I can cancel out this term. Then the work of the spring is half times k, 20, times x, which is 0.5 squared. Half of 20 is 10, and 0.5 squared is 0.25. This is 2.5 joules. Actually, questions about work and the SAT test are so simple as you know the formulas. You don't need to derive things because it's a multiple choice test, but I want you to understand how we got each of the formulas. But as you memorize them, it's so easy to solve all the related questions. Now, another important topic in this chapter is the work kinetic energy theorem. We said in the first example we did that the net work is the net force times delta D parallel. But there is another important formula to calculate the net work and relate that to the speed. That's the work kinetic energy theorem. Work net is the change in kinetic energy. This is the change in kinetic energy. Then work net is equal to half mv final squared minus half mv initial squared, because kinetic energy K or Ke is equal to half mv squared. Half mass times speed squared. Then the net work is half mv squared final minus half mv squared initial. We can substitute in this formula here to get F delta D, F net delta D equals half mv final squared minus half mv initial squared. This is a very important formula when you need to relate the force to the speed of an object. A 2 kilogram mass, the mass is 2 kilograms, moving at 4 meters per second. This is the velocity, 4 meters per second, which does 20 joules of work. This is the net work done on the object, 20 joules. Determine the final speed of the mass. We need V final, so this is V initial. The most appropriate formula to be used here is the work kinetic energy theorem, because it relates the net work to the speed of the mass. Work net is equal to half mv final squared minus half mv initial squared. The net work is 20 joules. It's half times the mass 2, okay, times V final squared, it's unknown, minus half times the mass 2 again, times V initial squared, that's 4 squared, it's 16. Don't forget to square it. This is a common mistake. Now, half of 2 is 1 and half of 2 is 1 as well. 1 times V final squared is V final squared minus 16. This is equal to 20. Move the 16 to the other side. This is 36. And it's equal to V final squared. Then V final equals the square root of 36, which is 6 meters per second. Look how simple it is when you know which formula to use for which question. Okay, let's go to more ideas. Work in uniform circular motion. In uniform circular motion, always the velocity is a tangent to the direction of motion, and for uniform circular motion, the speed is constant, the magnitude of the velocity and the centripetal force is always toward the center. If we apply the formula, work equals F delta D parallel or F delta D cosine theta, we see that the angle between the displacement, which is always along the tangent, and the force is always 90 degrees. Cosine 90 is 0. Then we can say that the work of the centripetal force in uniform circular motion is 0. We can prove that using the work kinetic energy theorem. Work net is equal to delta K, kinetic energy. It is half mv final squared minus half mv initial squared. This is the net work. V final and V initial are the same because the speed is constant in uniform circular motion. So the difference is 0 again. Sometimes they give you a graph like this, a graph of the force and the displacement, and they ask you to find the work of the varying force. A variable force acts on a 5 kilograms mass. This is the mass, it's 5 kilograms. Displacing the mass 8 meters. This is the total displacement. The force and displacement are graphed above. Determine the work done on the mass by the variable force. As we see on the graph, we have the force on the y-axis and the displacement on the x-axis. If we find the area of this graph, then we get the net work of this variable force. The area of the graph is the area of a triangle. It's half times the base times the height. The area of this graph is half times the base, 8, times the height, 4. The base is the displacement while the height is the force, and it's a variable force. That's why we need to take the area under the curve. This is equal to half times 8 is 4. 4 times 4 is 16 joules. Or Newton dot meter, as we are multiplying force times displacement. So when you have a graph of the force and the displacement, you can simply find the net work done by that force by finding the area under the curve. If you have a rectangular shape like this, you just find the area of the rectangle, which is length times width. You consider the shape you have, but mostly it is the area of a triangle. The last topic in this chapter is the power. The power is the rate at which work is done, or it could be also defined as the rate at which energy is transferred between objects. Then the power is the work over the time. It is the net work in a specific period of time. This is the first formula. The other two formulas are not new formulas. We can simply derive them from this formula. We know that the work is the force times displacement. This is F d over the time. Then this is the second formula. Displacement over time is velocity. And this is the third formula. Power is a scalar quantity, so we use the magnitude of the velocity, which is the speed. This is the third formula. Here we have two examples to apply the formulas of power. Determine the power required to lift a 10 Newton crate. This is the weight of the crate. Up to 400 centimeters. 400 centimeters is 4 meters. We need to represent the units in the fundamental SI units. In 2 seconds, this is the time needed. So I have the weight. And to lift anything up at a constant speed, you need to apply a force equal to its weight. Then the force is also 10 newtons. The time is 2 seconds and the displacement is 4 meters. Power is equal to Fd over T. The force is 10, displacement is 4, time is 2. This is 20 joule per second, and joule per second is a new unit. It is 20 watts. This is the unit of power. Determine the power required to lift a 10 Newton crate. Again, the force is 10 Newton vertically at a constant speed of 2. Here we have the speed. Then power is F times V. F is 10, V is 2, and this is 20 again. As always, there will be a link of a worksheet to upload in the description box to test your understanding. When you solve it, send the answers to my email or put them in the comments below, and I will put the correct answers after 2 days. That's all for today. In the next lesson, we will study momentum and impulse, and of course the conservation of momentum principle. See you next time.